In this class, we discuss about Dalton's law of partial pressures for gases. In the previous lectures, we discussed about the different gas laws, Boyle's law, Charles' law, Avogadro's law, and also the characteristic property of the gases, the diffusion, and the corresponding law, the Graham's law of diffusion. In continuation to it, another very important law that is proposed by John Dalton is the is the law of partial pressures. According to this, if you have a mixture of gases, in a mixture of non-reactive gases, the total pressure exerted by the mixture is equal to sum of the partial pressures of all the gases in the mixture. In a mixture of non-reactive gases like air, oxygen, nitrogen, helium, neon, argon, krypton, this kind of mixture if we have, then the total pressure exerted by the mixture is equal to sum of the partial pressure. What is partial pressure? Partial pressure is nothing but the pressure exerted by each component in that mixture. Means in a mixture of nitrogen and oxygen, if you take, the pressure exerted by nitrogen is the partial pressure of nitrogen, pressure exerted by only oxygen is a partial pressure of oxygen. The total pressure exerted by the mixture, suppose if you have a mixture of, example, in a mixture of nitrogen and oxygen, gases, if P1 is partial pressure of nitrogen, P2 is partial pressure of oxygen, and P is total pressure of the mixture, then P is equal to P1 plus P2, that is pressure exerted by nitrogen plus pressure exerted by oxygen. This is what the Dalton's law says. And like this, in any mixture of non-reactive gases, it is the same thing. Even if you have n number of components, means n number of gases in the mixture, then also this is applicable, provided none of the gases present in the mixture are reactive. For example, this law is not applicable for a mixture of reactive gases like a mixture of H2 and Cl2 and a mixture of ammonia and HCl, a mixture of SO2 and Cl2, mixture of carbon monoxide and chlorine. For these mixtures, for this kind of mixtures, this law is not applicable. The reason being that they are reactive. Ammonia and HCl, for example, if you take, you will get solid ammonium chloride. So that mixture is going to be converted into a solid. Or if you take this example, from 2 moles of mixture, if you are mixing carbon monoxide and chlorine in the ratio of 1:1, as the both are reactive, you will get only 1 mole of carbonyl chloride as the product, but you will no longer have the carbon monoxide and the chlorine as a separate entities. They both are reactive and you will get a single entity of COCl2, right. So you are no longer will have the carbon monoxide and chlorine as separate entities. So, this law of partial pressure is not applicable as long as they are not reactive. If you take the case of nitrogen and oxygen, obviously they are not reactive under normal conditions. For nitrogen and oxygen to react, we require a very high amount of heat. As we know very well, air consists of nitrogen and oxygen, which they are not reactive. If nitrogen and oxygen are reactive, we will not have nitrogen and oxygen as separate gases in the air. Then what we will get if they both are reactive? Nitric oxide. But you know, nitric oxide is formed with very high amount of energy being supplied. So, is the reason nitric oxide is the gas that is formed by the combination of nitrogen and oxygen during lightning. At that moment it is not, they both are reactive, but under normal conditions these are not reactive, because again some people may think that nitrogen and oxygen are also reactive, they will give nitric oxide, but they are not reactive. They are reactive only at very high energy during lightning. Under normal course they are not reactive. So, this law is applicable. So, under normal course whichever 2 or 3 gases are non-reactive, for all of that mixtures this Dalton's law is applicable. So, in general what we will say is, if you have a mixture of n number of gases, then P total is equal to P1 plus P2 plus P3 etc. Pn. Now, here once again the partial pressure of each gas is dependent on mole fraction of that particular gas in the mixture, because just simply if you say that P total is equal to P1 plus P2 plus P3 does not mean that P1, P2, P3 and all are same, because the pressure exerted by nitrogen and pressure exerted by oxygen and the pressure exerted by any other gas in the mixture depends on the number of moles of that particular gas in the mixture. Suppose nitrogen mole fraction is 0.1, oxygen mole fraction is 0.2, helium mole fraction is 0.3. Then obviously the pressure exerted by helium will be more than the pressure exerted by nitrogen and oxygen. So, this in turn depends on what? The mole fraction of the mixture, mole fraction of each gas in the mixture. So, that partial pressure, so P1 obviously will be equal to Xi into total pressure, where Xi is the mole fraction of that particular, or X1 sorry, for a first gas P1, that is pressure exerted by gas 1 is equal to mole fraction of gas 1 in the mixture into total pressure, P total, right. From, or the other way around is, if you are able to determine the partial pressure and the total pressure separately, then also what you can get is the mole fraction of that is equal to partial pressure of that divided by P total, that will give you the mole fraction. So, if mole fractions of each component is known, then we can determine the partial pressure of each gas as well as the total pressure in the mixture. Or if you know the partial pressure of each gas and also the total pressure, if you know the partial pressure of each gas, obviously also we know the total pressure, because sum of all that is nothing but the total. So, partial pressure of one component divided by total pressure will obviously will give you mole fraction of that particular component in the mixture. This is simple way that we deal this Dalton's law of partial pressures. Now, what are the more conclusions that we can draw from this Dalton's law, and what are its applications, and what more we can derive from this Dalton's law in the, now we look into it. Okay. So, this total pressure is equal to P1 plus P2 plus P3 etc. for a mixture of all the n number of gases. Now, also what the meaning is that this P1 is equal to X1 into P, P2 is equal to X2 into P etc. Pn is equal to Xn into P. So, the other way around, mole fraction of a particular gas I is equal to partial pressure of that ith gas divided by total pressure. So, that means Ni by sigma n is equal to Pi by P. So, from this the mole fraction and even the number of moles of each component also can be determined. This is what the Dalton's law of partial pressure is, right. Now, when it comes to the application, using Dalton's law, partial pressure of dry gas can be determined, partial pressure of dry gas or dry air can be determined if we know by knowing pressure of moist air and aqueous tension, because moist air is a mixture of dry air plus water vapor. Moist air is a mixture of dry air and water vapor. Therefore, according to Dalton's law, pressure of moist air, pressure exerted by moist air is equal to pressure exerted by dry air plus pressure exerted by water vapor. Pressure exerted by water vapor is what we call, therefore, pressure of dry air is equal to pressure of moist air minus pressure of water vapor. Now, pressure of moist air is nothing but the pressure what experimentally we can measure from the atmosphere, directly experimentally, practically we can what we determine. From that, partial pressure of or the pressure exerted by water vapor, if you subtract, you will get pressure of dry air. Then how do we get this? This is pressure of water vapor is pressure of water vapor, or this is what we call saturated vapor pressure of water is called aqueous tension, and it is constant at constant temperature. This is what we call aqueous tension. This aqueous tension is constant at constant temperature. Aqueous tension is constant at constant temperature. So, this value we can know it from the literature. This value we can know it from the literature, and this experimentally we can determine. So, from the experimentally determined value, if you subtract that value from the literature at a given temperature, you can determine the pressure of the dry air. Now, when it comes to the what is exactly this aqueous tension and what more that we can discuss on this now is what we will look into it. So, pressure of dry air is equal to pressure of moist air minus aqueous tension. Aqueous tension is nothing but saturated vapor pressure of water at constant temperature. With increase in temperature, aqueous tension increases. It depends only on temperature. No other condition will change this aqueous tension. It depends only on temperature, right? And why it is so and all, Actually we discuss about the vapor pressure of liquids in the liquid state also as well as in the liquid solutions topics. This vapor pressure is constant at constant temperature and this is saturated vapor pressure, so it is constant, right. But with increase in temperature aqueous tension increases. At 100 degrees Celsius, that is at boiling point, aqueous tension is equal to 1 atmosphere. At boiling point of water, aqueous tension is 1 atmosphere because the whole liquid evaporates at that particular temperature, or in other words boiling point is when we define the basic definition of boiling point is it is the temperature at which vapor pressure of a liquid becomes equal to atmospheric pressure. So, aqueous tension, which is nothing but vapor pressure at boiling point, obviously will be equal to atmospheric pressure, so it is 1 atmosphere. So, if you subtract, so at 100 degrees Celsius you can write that pressure of dry air is equal to pressure of moist air minus 1 atmosphere, right. So, this is one, and also using this also we can determine the relative humidity in air, relative humidity in air. How do we determine? Relative humidity RH is equal to pressure of water vapor in air, that is partial pressure of water, divided by aqueous tension into 100. Relative humidity, which we regularly listen in the weather reports. Relative humidity is nothing but which gives us about the percentage of moisture in the air. Percentage of moisture in the air is nothing but relative humidity. Relative humidity means percentage of water in the total air. Percentage of water in the air, relative humidity is equal to pressure of water vapor by aqueous tension into 100. That will give you, because this aqueous tension is a saturated vapor pressure where you consider that whole air is consisting of water vapor, in relative to that, that is say 100, then what is it? What fraction of it? So, this gives us the relative humidity. And also what we can determine using this is, if once you measure the partial pressure aqueous tension, then also we can say that whether a given salt is the hygroscopic nature of the salt, whether the salt is efflorescent or not, whether a given salt is efflorescent or not, also we can determine. Efflorescence means whether salt absorbing water vapor is what we call efflorescence. If the partial pressure of salt, mean hydrated salt like CuSO4 5H2O becomes CuSO4 plus CuSO4 dot 2H2O plus 3H2O vapor. Now, for this equilibrium constant, it depends on the pressure of water vapor. If this is pressure due to this water vapor is less than aqueous tension, then the salt is efflorescent, it still can absorb water. Or if this is greater than the aqueous tension, then it will release water vapor. Then, so whether the salt is hygroscopic or efflorescent, if this pressure is, again I am repeating, if this pressure is less than the saturated vapor pressure of water, that is aqueous tension in the air, still it can absorb water. So, that in that case it will become hygroscopic, still it can absorb. But on the other hand, if this is more, that means this cannot absorb any more water, or rather it will give out water to the atmosphere. In that case, that means it is a fluorescent, right? And in that process, some salts also will appear in different colors, they will give light. So this is what we call hygroscopic and a fluorescent. So using this Dalton's law, or the main application of Dalton's law is that we first of all we can determine the pressure of dry air, we can determine relative humidity, we can determine whether the salt is a fluorescent or hygroscopic or not. These are all the things what we can understand, what we can determine by applying the concept of this Dalton's law of partial pressures.